Okay, so uh, let's talk about another section, sigma notation and the limit of the finite sum. Okay, um, the main focus will be the sigma notation. Okay, the limit of the finite sum. I might touch one example, and then also um, there's another concept called the Riemann sum, which build the bridge between the limit of the sum and the definite integral. I'll briefly talk about it later on. But let's look at this, guys. We introduce a new notation. It's called the sigma notation. You know, when we have the summation of a lot of terms, right? And if you think about it, the previous section when we introduced using the area of the rectangular to do the approximation for the area under the curve, right? And you see as the partition numbers goes high, and then the you're gonna add a lot of small areas together. So how do we write it into a more clean and efficient way? Well, sigma notation. This is how do we determine. If we have the sum of n terms and we denote it as a1 plus a2, a3, up to an, and this is what we call a sigma notation. This is the sigma, and this is the starting index k, meaning that k starting from 1 up to n, okay? And then for here, this is the case term, okay? When k equals 1, stands for a1. When k equals 2, this is a2. When k equals 3, a3, up to an, okay? When k equals 1, which is an. And again, sigma notation is the sum, okay, the sum. For example, let's look at those examples here. We have 1 plus 2 plus 3, up to 100. And there we have 100 numbers, right? So how do we write it into a sigma notation? Well, we write the sigma notation here first, okay? And we can let our starting index k equals 1. But in this problem, do you agree that this n gonna become into 100? Because I only have 100 numbers added together. And for here, guys, be very careful. K actually is a variable, okay? You are starting to do the dancing here. And, when k equals 1, I have 1. When k equals 2, I have 2. When k equals 3, I have 3, etc. So, put a k here. Okay, so we're done. Easy, right? Now let's look at this one. 1 squared plus 2 squared plus 3 squared up to 11 squared. As you can see that the number of the terms, you have 11 terms added together. So this is what we can do. We can draw the summation sign. Again, k starting from 1 up to 11, right? Because we have 11 terms added together. And then the corresponding case term, it's gonna be k squared, right? Because when k equals 1, 1 squared. When k equals 2, 2 squared. When k equals 3, 3 squared. Up to 11 squared. So that's how do we do this. Okay. All right. So I believe right now you already have some brief ideas, right, about the sigma notation. Let's look at another one. 1 over 2 plus 2 over 3 plus 3 over 4 plus 4 over 5, up to 99 over 100. So first of all, first question, guys. How many terms we have during this summation? Now, you can think about it in two ways. First, you can start to do the counting for the numerator, right? So 1, 2, 3, 4, up to 99. So we have 99 terms. Or you can do the counting from the denominator part. 2, 3, 4, 5, up to 100. If you have those consecutive numbers, and then how do you do the counting? Fairly easy, guys. use the last one, subtract the first one, and then plus 1. That's the number of terms you have. For example, we have 99 minus 1, and then plus 1, it gives us still 99. If 100 minus 2, and then plus 1 give us is 99. Okay, so that's how you do the counting. So if we write into the sigma notation here, we can do k equals 1 here up to 99 because we only have 99 terms. All right, so now how do we write the kth term representation? As you can see, guys, when k equals 1, I have is 1 over 2, right? When k equals 2, so this is k equals, this is k equals 1, when k equals 2, when k equals 3, when k equals 4, right? This is when k equals 99. Do you see the pattern, guys? You know that the kth term is definitely gonna be a fraction form, and the numerator, do you see, it's always k, right? What about the denominator? Take a look. When we have 1, you give me 2. When I have 2, you give me 3. When I have 3, you give me 4. What's the pattern? Do you realize that it's always k plus 1? So we know, okay? So that's about the sigma notation here. All right, so now let's move to the other side. Okay. So one note here is when we're trying to write the sigma notation here, the starting index, in the previous example, we see that we started from 1. But actually, guys, the starting index can be any number, okay? I mean, as long as it's greater or equal than 0, okay? Greater or equal than 0. You can start from a negative integer, but, it's probably not that fun. So let me just introduce a little bit about it here. So look at this. We have 1 plus 2 plus 3 plus 4 plus 5. And if we write it into the sigma notation, and the starting index is k equals 1. Okay, k equals 1. This is what we can do, right? So k equals 1. And we know that we have 5, right? And then we can put it here as k. Agree? Right? So k equals 1 is 1, 2 is 2, 3 is 3, 4 is 4, 5 is 5. Perfect. What if we let our starting index is 0 instead of 1? Okay. But we still can handle it. Okay. So when k is 0, and you see all this index is gonna be integers, right? So if you start from 0, we need to find numbers. Let's see, we have 0, we have 1, we have 2, we have 3, we have 4, right? So we put our upper index as a 4 here. And then let's see how do we represent our k terms. When k equals 0, I have 1. When k equals 1, I have 2. K equals 2, I have 3. K equals 4. K equals 3, I have 4. K equals 4, I have 5. So do you see that? If we represent this in the sigma notation here, starting index is 0, it's gonna be k plus 1, right? Because when k is 0, 0 plus 1 give us is 1. Great. When k equals 1, 1 plus 1 is 2 is good. When k equals 2, 2 plus 1 is 3. When k equals 3, 3 plus 1 is 4. When k equals 4, 4 plus 1 is 5. Done. Okay, so just to let you know that those sigma notations, the starting index is not unique, but starting from k equals 1 or 0 are the two very common starting index. Okay. Also, look at this. There are some properties which is very easy to understand. If we have the summation, so the summation of, if we have sigma notation inside part, it's the summation of two pieces. So AK plus or minus BK. You actually can split them into two small summation parts. Okay. So this is the first property. For example, if we have something like this, if we have, I don't know, so k from 1 to n, if we have k plus k squared, something like this, you can always rewrite this k from 1 to n k, and then plus the summation k from 1 to n k squared. Okay, so this is one of the applications. Example here. Okay, so this refers to this one. Now this one here, if we have summation c arbitrary constant time, I should put it here as ak. Okay, my bad. So it's ak, and then you can always take the constant outside of this summation. So, for example, if we have, let's see, I don't know, so 3 times k cubed, okay, k cubed. And, we can always rewrite this into 3 times the summation k from 1 to n k cubed. Okay, so again, constant you can always pull out. Last one. So k from 1 to n c. Okay. Now let's really think about this. What does this mean? C again is an arbitrary constant. Do you realize that, guys, your kth term is a constant, meaning you are adding n c together, right? Think about this. When k equals 1 is a constant. When k equals 2 is a constant. When k equals 3 is constant, up to n. So basically you have a c plus c plus c plus plus c, and then you have n c's, right? So the sum is n times c. Okay, n times c. So this is the first part for 5.2. Okay, so I'll stop here.